Okay, good morning. We're well into our way studying rotation matrices. So today I want to continue where we left off last time and show you another way to parameterize rotation matrices, this time using exponential coordinates, which are based on linear differential equations. Okay? So let's first review the highlights from last time. Okay. So there were basically two main results. Okay, so we started off with a formula for rotation matrices. Look like the following. Okay, so we had this formula. So an arbitrary rotation matrix R is written as the product of three rotations. Rotation around the z-axis by alpha. Okay, this is a 3 by 3 rotation matrix whose form you know. This is a rotation around the y-axis by beta. And then this is a rotation around the x-axis by angle gamma. Okay? So there are two interpretations, okay, of this formula. Okay, so the first interpretation is the Euler angle interpretation. Okay, so what we're doing here is we start off with a frame. Okay, moving frame. Here are the x, y, and z axes. We first rotate this frame around the z-axis by an angle alpha. Okay, so if we do that, we'll get some rotation. So x will rotate to some vector here. Y will rotate to some other vector here. And z will stay the same. Okay, so z will stay the same. Okay. And then in the next step, we now rotate this yellow frame. Okay, let's call this x hat prime, y hat prime, and this is z hat prime. Okay, so now we rotate this frame around the y prime axis. Okay, by an angle beta. Okay, so now this rotates to another frame. So we can imagine, okay, something like that. So this will be z double prime. This will be x double prime. And y double prime will essentially remain the same. Okay. Okay. Now in the third case, we now rotate. So, okay, now let's draw this. So we have y double prime here, x double prime here, z double prime here. Now we rotate around the x double prime axis by angle gamma. Okay, so here's angle gamma. And when we do that, Okay, the x double prime axis remains the same, so x triple prime is the same as x double prime. But now these two rotations, these two axes, y double prime and z double prime, rotate to some axis as shown. Prime, z triple prime. Okay? Okay, so this white frame here, that's R. That's what we get. Okay, so you follow these three sequence of rotations. And they're all rotations about the moving frame axis, okay? Z followed by y followed by x, okay? So three rotations about the moving frame, z, y, x. Okay, that's what you get here. Okay. So if you think about the wrist, okay, so let's draw our wrist again. Okay, so there's our wrist. Okay, and okay. So let's draw the effector frame here. There's the tool frame. Okay. Let's do this. Okay. So let's rotate around the z-axis by alpha. Okay. What are we doing? That's just rotating this axis, this joint by alpha. Okay. So rotating alpha is the same as rotating this end effector frame about its own z-axis. Okay, so we do that. Next, we rotate about the y-axis. Okay, rotate around z first. Next, we rotate about the y-axis. What's that? That's just rotation of this joint. Okay. Rotate, rotate. Finally, we rotate about the x-axis by gamma. Okay. So you see that the rotations I've drawn here, the sequence of rotations I've drawn here, exactly match the rotations, okay, alpha, beta, gamma in this sequence for this wrist. Okay. So it's really the same thing. Okay. So that's why I motivated this this Euler angle representation using this wrist mechanism. Okay. So here's one interpretation. The other interpretation that I showed you last time is the following. So let's draw a fixed frame first. Okay, so here's a fixed frame. Now let me draw a frame here. Okay, and this is the fixed frame. So we're going to use large letters, large X, large Y, and large Z to denote the fixed frame unit axes. First, we rotate this yellow frame around the fixed frame x-axis, okay, by angle alpha, angle gamma, sorry. So when I do that, I'm going to get something. Okay, so it'll probably look something like that. Okay. Okay, next. So now I have here's the fixed frame again. Y, Z. Okay. So now I have my red frame. I'm going to rotate this red frame around the fixed frame y-axis, okay, by angle beta. Okay, so if I do that, I'm going to get, okay, now we're going to triple colors. I'm going to get something, I don't know, something like that. Okay. And then in the last sequence, I will now rotate let's try the fixed frame one more time. Okay, so let's see what the blue frame orientation looks like. Okay, something like, roughly like that. Okay, and x, y, z. Okay, last case, I rotate this blue frame around the z-axis by angle alpha. Okay, to get, let's go back to the original color. I don't know, maybe something like, oops, sorry about that. Try to do a better job. Okay. All right, so in the second case, the sequence of rotations was reversed, okay? And the rotations were done with respect to the fixed frame axis, okay? Okay, so what I showed you last time, okay, the main result, one of the main results, was that the final orientations indicated in yellow here and the orientation for the Euler angle are the same. Okay, so one formula, two ways to get there. Okay, one is rotating with respect to the moving frame axes, z-y-x. The other way to get there is rotating with respect to the fixed frame axes, x, y, z. Okay, all right. So these are the Euler angles. These are the fixed axis angles. Okay. Same formula, two interpretations. Okay, so that was one result. The next thing I want to do is I want to just sort of list the main results about linear differential equations that we derived last time, because we're going to be using them today. Okay. Some results from linear differential equations. All right, so the equations that we're interested in are of the form x dot equals ax. Okay, so x here is a n-dimensional vector. Okay, A is an n by n matrix, and we're going to assume it's constant. Okay, and let's assume that the initial conditions are given at 0. So x0 is given. Okay, so last time we managed to write down a solution for this equation. Okay, in the form, in the following form. So the solution involves a matrix exponential. So x of t, okay, is equal to e to the at times x0, where e to the at is a matrix, okay, and it's defined as an infinite series, I plus at plus a square t square 2 factorial plus a cubed t cubed 2 factorial plus dot dot dot. Okay? Okay, so we verified that this is a solution by plugging it back into the original differential equation, making sure that it satisfied both sides. We also proved some properties. Of this matrix exponential. The first is that, let's see. The first thing we showed was that if D is a diagonal matrix, okay, then its matrix exponential, e to the dt, is another diagonal matrix, okay, e to the d1t, e to the dn t. Okay, so if A happens to be a diagonal matrix, it's particularly easy to find its matrix exponential. So why is this useful? Well, it's useful because if A can be written in the form P times D times P inverse, okay, that is A is diagonalizable in this form, then e to the at is simply P times e to the dt times P inverse. Okay, so we showed this, again, using the definition, the series definition of a matrix exponential. Okay, so with this result, it's quite easy to calculate the exponential, e to the at, okay, because e to the dt is particularly easy to compute. Okay, so we showed that. Third thing we showed was in the course of verifying that this was a solution, we showed that a times e to the a t is equal to e to the at times a. Okay, so in general, when you multiply two matrices, A times B, order matters. A times B is not the same as B times A in general. Okay, but in this case, order doesn't matter. Okay, in fact, we can write a slightly more general version of this result. Okay, if A times B, given two matrices, square matrices, A and B, if A times B is equal to B times A, then it turns out that e to the A times e to the B is also the same as e to the B times e to the A. Okay, and in fact, order doesn't matter, so we can just write this as e to the A plus B. Okay. All right, so again, a more general version of number 3 is number 4. Okay, so 3 is just a special case of 4. How can you verify this? Well, one way to do it is to use the definition, series definition of the exponential. Write it out, match terms. Okay, it's a bit of work, okay, but doable. Okay, and the fifth property is that if I want to take the inverse of e to the a, okay, turns out this is quite easy to do. It's just e to the minus a. Okay, and this follows from the fourth property. Okay. In fact, the arrow goes both ways here. Okay. All right. So this is where we left off last time. Now, properties number 4 and 5, I didn't really show you last time. Okay, but I think you know how to get there. So if you have a chance, please take a look at the relevant section in the text. Okay, for a discussion of those two further properties.